Okay, it's 12:01. Let's get started. This webinar is recorded. So welcome everyone. This is a webinar from a pollution prevention webinar series. The title of the webinar is Two Inexpensive Tools of Energy Management, Data Loggers and Thermal Imagers. So this is part of the center webinars, the Center for Sustainability, Energy and Environmental Engineering. Promote, enhance, and serve is the mission of the center, and this is part of what we do at the center. EPA pollution prevention program, source reduction assistant, SRE. So we do on-site energy P2 lean assessment, regional and on-site P2 energy training. We do a lot of workshops, technical and engineering supports, and also cash flow and market analysis, return on investment. My name is Carol Masarra. I am an assistant professor in the Department of Construction Management and also the director of coastal resilience at the center. Our speaker today is Mr. Ralph Nigro. He is an assistant director of the Mid-Atlantic Industrial Assessment Center at University of Delaware. Ralph is a mechanical engineer with 42 years of experience focused on energy systems. His background and experience include power generation and CHP, industrial boilers and steam systems, and industrial energy efficiency. Ralph spent 15 years as a project and planning engineering with Delaware Power and Light, working on numerous power generation construction and improvement projects. This was followed by a 25 years with Applied Energy Group, a consultant in in residential, commercial, and industrial energy efficiency, and finished his career as a senior vice president for technical and implementation service. Ralph is going to talk about two inexpensive tools of energy management, portable data loggers and thermal imaging cameras. So as I said, the webinar is recorded. Please make sure that your microphone is muted during the presentation. If you have any question, you can raise the hand icon or write your question in the chat. After Mark finishes his presentation, we will open it for Q&A session. Thank you again for joining us, and I will turn it over to you, Ralph.
Thank you, Carol, and good afternoon, everybody. And before I start, I would just like to thank East Carolina University, Dr. Masarra, Dr. Abdul Salam, Ariel Lineweber, and Grace Jacobson for setting this up and presenting this. So today we're going to talk about two tools that I use a lot in my industrial auditing work, and these are just data loggers and thermal imaging cameras. Just a brief agenda. I'll cover a little bit of the overview, background. We'll talk about data collection and why we do it for energy management. Data logger installation and data analysis, some examples and brief case studies of how we use them. And then we'll segue into thermal imagers and their uses, and then a very brief wrap up. So a little bit of the background information. The Mid-Atlantic Industrial Assessment Center is part of a US DOE program. We cover a region that includes Delaware, most of Maryland, southeastern Pennsylvania, southern New Jersey, and northern Virginia. And I'm the assistant director, as Carol already mentioned. We have a pretty straightforward mission, and that is to provide no-cost energy and waste assessments for small and medium-sized manufacturers. We train engineering students to perform these assessments and identify and analyze opportunities for energy and waste reduction. And we serve, in this case, both industrial and the nonprofit sectors, including schools, churches, community centers, and similar facilities. One of the things that we always encounter, with very, very few exceptions, I would say, is every facility that we visit wants to know where their energy is used, but they more often than not don't know how have the means to measure it. And there's a very common saying that you can't control what you can't measure. So we help them to solve that problem, at least to the extent that we can. Next slide, please. The reason for this, the reason that it's not very easy for many facilities to get more of a handle on this is they're resource constrained. They may have small staff. They're focused particularly in manufacturing on maintenance and operations. They don't have a systematic or centralized data acquisition. And as always, money is a factor. So before we go too deeply into how to measure where the energy goes, we should always ask ourselves the question, what's the goal? Why are we doing this? And very simply, if you know where and how you can start managing costs. That's really the critical link between energy usage and then the bottom line dollars for the facilities that we go into. And typically every plant or facility knows what is being supplied by the utility or bills, but they don't necessarily know where it goes. So the key to this is doing a bill disaggregation. So what do I mean by that? Next slide. So if you look at this slide, this is from a recent assessment that we did. Utility bills are pretty simple in this case. And what I did was I normalized everything to millions of BTUs for both electricity and natural gas. So they know how much they're using in aggregate of each fuel, electricity and gas, and they know how they're spending. In this case, it's about $2.4 million per year in total, but they don't really know how it's used inside their plant. The next slide. So this is where we're trying to, this is what we're trying to achieve. We're trying to get to a disaggregated bill on at least an annual basis so that they can spot where most of their energy expenditures are going. Ideally, every plant should know at least this much. What are the major end uses inside the plant and how much energy is used by them? And for an example, in this case, the plant thought that their air pollution control equipment accounted for a much larger share of their electricity usage and that air compressors were insignificant. But in fact, the opposite was true. So how do we get to this point and what do we do with this information? The next slide. So this is where data loggers come into the picture. Next slide. So what we use are very small, simple, inexpensive data loggers. In this case, these are supplied by a company called Onset. And they allow us to do what's needed, basically to disaggregate the utility bills, and that helps to guide us to the problem areas and most importantly to what the solutions are for those problem areas. So in our work, we almost exclusively use our data logs to measure electric current in order to break down electricity usage. But there are a very wide variety of sensors that can do other things, and there are specialized data loggers. Sensor types besides current transformers include voltage sensors, thermocouples. You can monitor analog instrumentation signals. You can get on-off sensors, light loggers. There are all sorts of options available for these data loggers. And they're, as I mentioned, they're inexpensive. Each logger costs anywhere from $150 to about $300. The current transformers range from about $40 to $70 each. So the complete setup that you see in that picture was about $200 or a little less, actually. Actually, could you go back to the previous slide? Yeah, okay. So a few of the pros and cons. The one thing I'd like to say is that these are not a panacea. There are good reasons to use them, and there are also reasons not to use them. On the pro side, inexpensive and simple. Very high data resolution is possible. We can monitor with these data loggers at fractions of a second if necessary. They're great for troubleshooting, even if equipment's already being monitored by a centralized data acquisition system because of the resolution that we're able to achieve. And again, they have a wide variety of sensors, so they can measure lots and lots of different kinds of data points and variables. On the con side, are normally used for long-term measurement. They also have to be installed and then removed to download the data. Because we only get a snapshot in time, annual usage has to be estimated or projected. And they're also not really practical for plant-wide measurement. Some of the latest equipment is capable of being networked using Bluetooth or Wi-Fi, but we don't use these because in most plants, they're electrically noisy, and it's not easy to get a reliable connection between devices. Also, in using Wi-Fi, most plants don't like the idea of somebody coming in and connecting devices to their Wi-Fi network or accessing their Wi-Fi network. So we use standalone data loggers for the most part. Okay, so the next slide. All right, so how do these fit in then, given the pros and cons? So first thing is consider called the measurement hierarchy. High-level utility data is continuously collected, but it provides only total consumption and peak demand information. Secondary meters or submeters can be used to measure subsystems or even individual plant equipment usage. Similarly, detailed equipment usage may be collected by a factory automation or a DAS, data acquisition system. Some larger plants that we visit have types of systems, and they can easily determine where their energy is going. But in most cases, and in those cases, we're able to help them identify efficiency opportunities pretty quickly. But most small plants don't have submetering or data acquisition systems. And that's where data loggers come in. They bridge that gap between the continuously monitored equipment and unmonitored equipment. And so through a combination of using data loggers and engineering estimates, we can then determine how much the major end uses are consuming. Next slide. Any of you who have worked in a laboratory or have done any kind of experimentation at all know that before you start collecting data or start doing what it is you set out to do, you have to have a plan. And so we always consider what questions we want to answer before we start collecting and analyzing the data. And that's our data collection approach. Most of the time, we will start by looking, and this actually happens before we go to a plant site. We start with monthly utility bills, and we look for seasonal variations, correlation to production levels, unexplained increases or decreases in total usage or in peak loads. Once we get onto the plant site, we start interviewing the plant personnel, and we ask them what they think could be the biggest contributors to usage and peak loads. And then from that collection of information, we identify the end uses for monitoring. So for example, it may be the largest motors on site. Secondary utilities like air compressors. It could be aggregated smaller loads where there are multiple units like refrigeration compressors, hydraulic skids, lighting, HVAC, a whole range of different things that could be incorporated in that. So this is basically the plan to collect and analyze the data. In other words, what are we targeting? And then we get into how to analyze it. So the next slide. If you have not done this yourself, and if you're considering doing something like this, the first piece of advice I would offer is that less is more. There's a little bit of an art to determining what to monitor and making the data collection work. So, for example, if there are a lot of but similar pieces of equipment that you think might be contributing significantly, try out a sampling strategy. We once assessed a plant where there were over 20 hydraulic pump skids. We selected 2 of them for monitoring, and then we were able to make a projection from that of how much total energy was used by the rest. You can do the same thing where lighting might be a significant end use. Often that's not the case in manufacturing, but sometimes it can be. In most cases, we monitor for 1 or 2 weeks at a plant. We're limited by when our assessment takes place, but we always make sure we understand how typical our monitoring time frame is in comparison to the plant's normal production schedule. Data resolution is important, and that's basically the time interval between measurements. For measuring current, and this is especially true on air compressors, we choose a very high resolution every 5 or 10 seconds typically. And that's in loading and unloading patterns. Other equipment may not need measurements as frequently. If you're measuring slower moving variables like temperature, you may be able to select a time interval that's 15, 20, 60 minutes, or even a day. Sometimes that's for some measurements, you may not need anything more frequently than every 24 hours. And then after that, you identify the equipment that you need to collect in order to do that, with how many data loggers, current clamps, and so forth. So before I go into the nuts and bolts of these data loggers, I just wanted to talk a little bit about electrical safety. If you think about using this kind of equipment, the first thing to remember is that safety is very much at the top of the list. The first thing I should say about that is whatever your plant safety procedures are for opening and working on electrical equipment, they should be followed. Whenever we go into a facility, we always respect what the plant requires when it comes to safety procedures. And if that means getting somebody else from the plant staff to do the installation work, we do that. We work with them and we show them where we would like our data loggers installed, and then they do it for us. Another thing that is important here is that our IAC only installs data loggers on equipment operating at 480 or less. And that's for 2 reasons. One is that the current transformers are rated for 600 volts or lower. So they're not qualified for use on higher voltage equipment. And the second thing, which I didn't put on here, but I probably should have, is that working on anything higher than 480 usually means that you're going to be exposed to voltages that can be well in excess, 2400 volts and higher. And that really takes specialized training and equipment to work on. So keep in mind electrical safety always when you're doing this. Next slide. 2 kinds of measurement scenarios, and the most common one is direct measurement. In those cases, we'll install current transformers usually on the load side of a disconnect switch that's feeding a piece of equipment. And those current transformers are selected based on the maximum running amperage of the equipment. It's okay to put a current transformer on that's higher than the expected running level. Even if it's low, necessarily a safety issue, but what will happen is you'll get data at the upper end that will show a flat line because the current transformer won't be able to, it'll saturate and it won't be able to record and give you an accurate reading. So a little bit of math may be required to do that if you know how to calculate running amperage given voltage and power rating of the equipment, then that enables you to select the current transformer. It's also not necessary on a 3-phase system to monitor all 3 phases. Just monitoring one is sufficient. So the second way of measuring is an indirect measurement. In some cases, you can't monitor a load directly, and that includes loads operating at greater than 480, or there may be access limitations. There could be any number of reasons. So we've been able to, in some cases, use workarounds or identify some sort of a proxy measurement, and they might be monitoring on-off or analog control signals. In some cases, for example, boilers where gas is not metered, we've been able to estimate gas usage by monitoring a piece of auxiliary equipment such as a burner fan or a feed pump. On large compressors or drives, there may be cooling fans that operate in parallel with the equipment. So there are a number of ways that you might be able to get around it in a case where you can't necessarily get a direct measurement. Next slide. So now we get into processing and interpreting the data. I mentioned that we use onset equipment, and if you're not familiar with that, it's ONSET. Onset makes data loggers and software for this purpose. The software for most data loggers is proprietary, whether you're using Onset or Fluke or any number of other manufacturers. That's needed to set the data loggers up and to record data. In the case of the Onset software, they include graphing and other functions. Regardless of whose system you're using and what software they have, all of the ones that I know about have the option to export data. And once you download that data, Excel is your friend. Anything that you can do in Excel is accessible. All you have to do is export a CSV file, or in some cases, it may be directly an Excel file. You can process, you can graph, you can analyze using all of Excel's available tools. Next slide. So now I'm going to describe the two basic approaches that we take to analyze the data. The first is very straightforward, simple time series analysis, and that's where data is graphed and analyzed in the order in which it's collected for each time interval. And that, I think, everybody has probably done something like that when looking at sequential data. The other means of analysis that we employ is called load duration. In that case, data is graphed and analyzed from the highest value to the lowest value. So it's similar to a frequency distribution, and I'll explain that in some examples. Next slide. So here's an example of a time series analysis. This involved a 125 horsepower screw compressor with inlet valve modulation at a food processing facility. If you're not familiar with what I mean by inlet valve modulation, it's basically a throttle valve on the inlet of the compressor to control the amount of compressed air that's discharged. It's a very inefficient way of managing a compressor, but nonetheless, they're still out there, and a lot of plants still use them. So in this case, we did current measurement over 10-second intervals for about 8 days. And in this case, what we found just by looking at this data is that the compressor never stopped. It operated at minimum load much of the time to supply what turned out to be a couple of very small control valves in one room during non-production hours. And what we found from that data is that about 12% of the total plant electricity usage was due to the compressor running at minimum load with virtually no output. So what we and what you can see in that graph is where the flat lines are, and that red arrow says compressor running at minimum load, nearly zero output. That's where it was running most of the time. And then you can see those bumps up, and that's where compressed air was used mainly for filling and packaging operations. And that was a fairly typical 8 hours, actually a little bit longer, I think, in this case. And then the compressor would go back to running at minimum load. So this pointed us to the solution, which was to isolate those control valves and use a small pony compressor and shut down the main compressor after hours. The plant implemented this because the savings were very high for a very small investment. Another recommendation was, if capital was available, then a better option for the whole plant was to use a variable speed drive compressor, but at least they could get some significant savings by a pony compressor and just simply shutting down the larger compressor. Next slide. And this is an example also on a compressor, in this case, a variable frequency drive compressor, of a load duration analysis. Same scenario, measurement scenario, 10-second intervals, about 8 days. In this case, the plant told us that the VFD compressor was installed to take swings in the plant air load, which is an ideal application for a variable frequency drive. But what this analysis shows is that it ran at an average of 91% of its capacity. The further data from the other plants, other compressors also showed that the air system was running at just about full capacity all the time. And that was due to a leakage rate in excess of 40%. The same analysis also showed we had about 11% of the plant's electricity usage was just due to compressors. The recommendation in this case was very straightforward. You got to repair air leaks and you got to perform regular leak checks. Otherwise, you're costing yourself a lot of money. The plant certainly understood that, and they implemented a regular leak protocol, and they were able to repair a significant number of at least the major air leaks in the plant. So it saved them considerable money. These curves can vary a lot depending on what you're monitoring. I would say this is atypical. More often than not, they'll have a sharper spike on the left-hand side, and that represents the highest short duration loads. Then it's followed by a plateau, and that represents average or typical load. And then there may be a gradual, or in some cases, a sharp fall off like this one. Next slide. Quick note about measuring variable frequency drive loads. When you're using current clamps and data loggers, you have to measure AC input to the drive, not the variable frequency drive output to the motor. And that's because VFDs use what's called pulse width modulation, which varies both frequency and voltage to the motor. And so current readings alone don't accurately reflect the power input to the motor. So you have to measure it on the input side, not on the output side. So that's a quick wrap up of the data logger component. So we're going to segue to thermal imagers. Next slide. So thermal imaging equipment very basically detects the amount of infrared radiation emitted by an object, and that the intensity of that radiation is proportional to the temperature of the object. What the imager does is it converts that infrared radiation signal into a visual representation of an object's temperature. And I'll show you in the upcoming slides what that looks like on the imager. Couple of basic types. We use a general purpose imager, but there are imagers that are designed for building diagnostic purposes. Energy auditors use that to look at things like insulation levels, moisture in insulation, things like that. They're geared specifically to building auditors. And by buildings, I mean residential and commercial buildings for the most part. There are fire and rescue imagers that are used for that purpose to detect, for example, where people might be in a smoke-filled environment. And there are also optical gas scanners that are used to detect gas leaks like methane and sulfur hexafluoride. Next slide. So general purpose imagers is what we're going to focus on. Wide variety of sizes and capabilities. Most common resolutions are 160 by 120 or 320 by 240, and that's on the infrared resolution. Most of them also have a higher resolution digital camera for visible light photographs, so it provides a background photo overlaid by the infrared image, the IR image, so that you get more context of where you are and what piece of equipment you're looking at. Less expensive models typically measure from about -4 to about 800 degrees Fahrenheit. They can include a wide range of features. They can include time lapse or automatic triggers, picture in picture. They may be fixed, manual, or autofocus. Most of them automatically scale and allow you to also manually scale. Adjustable emissivity settings are very common. A basic model from a good manufacturer will start at about $2,500, but costs can go up very quickly as resolution and the upper temperature limit increase. Higher end imagers can cost dollars or more. What we found, and we had a higher resolution imager at one time that was a donation from a supporter of the center. And what we found, it failed unfortunately, but what we found is that the higher resolution really didn't give us better data in terms of its usefulness. It may be more useful in certain instances, but for the kind of work that we do, we really didn't need to go to high resolution. One last thing is you can now buy imagers that can connect to a smartphone for a few $100s. I don't know much about them. They're very inexpensive, so they may be worth checking out if you want to kind of dip your toe in the water and try this out without committing to a couple $1,000s for an imager. Next slide. So this is the imager that we use, manufactured by Fluke. There are other makers out there like X-Tech and FLIR, F-L-I-R. The one that we have is 320 by 240 resolution. It has picture-in-picture. You can do automatic or manual scaling. And in this case, it's fixed focus. The previous model that we had was much larger, much heavier. It allowed adjustable focus, but again, we found out that we didn't miss it that much. Manual focus is fine as long as you're not too close to what you're imaging. And in this case, it's also capable of automatically capturing images at preset temperatures. So you can set it up on a tripod in front of a piece of equipment that you think might be causing you a problem. And you can preset the temperature at which it'll take the image. And so once it crosses the threshold, you'll get an image of what's going on. Sometimes it's useful, and we don't use it much, but we have in the past on occasion. Next, okay. So most common applications are visualizing thermal energy losses through insulation, piping, and so on. Pinpointing electrical and mechanical problems. Thermal imagers are used a lot to look at things like electrical switchgear and connections to see where there may be loose connections. They'll typically have a higher resistance, which means more heat, and you can visually see where electrical components may be overloading. Mechanically, it can detect failing bearings and motors by looking at temperatures. You can detect failing or wet insulation. You can detect failed steam traps. So they have a variety of uses that make them well worth it. Next slide. So now a couple of examples. And before I go into the details of this, one of the reasons that I really like thermal imaging is that it's a very powerful visual tool. Humans are visual creatures, and we respond a lot to what we see. And it's these images can really provide a lot of information very quickly to our clients. In fact, one of our clients once said to me, "I can almost feel the heat by looking at the picture." In this case, we're looking at a drying oven, paint drying oven that's installed at a metal products manufacturer. The picture on the left shows the oven roof insulation, and what we're seeing is that the temperature on the oven roof is over 270 degrees, approaching 300 degrees. And the reason that it was that high is because the insulation in the roof was failing because the roof of the building above was leaky, water was getting into the insulation, and the insulation was deteriorating. So it presented not only an energy loss issue, it also was a personnel safety issue because there were people who had to go up there and work in areas around the roof of the oven where it got terribly hot. The underside of that oven also showed some problems where there were hot spots, and that was caused by deterioration of internal support components that was also allowing moisture, and there were a whole host of problems that were allowing heat to get through the insulation, around the insulation, and out into the structural components and causing all sorts of problems for them. So in this case, the plant, once they saw this, they had the information they needed to justify re-insulating the oven at the next overhaul, which is about the best outcome that we could have expected. Next slide. This was a little bit more of a serendipitous event for us. This was a plant that manufactures plastic film. It's a fairly hot plant. They had heaters located in the overhead of the building. In fact, I think there were around 25 of them. And the plant decided they no longer needed them for space heat. So they disconnected the controls, but they didn't isolate the steam to the heaters. So even though the fans weren't running and the thermostats weren't calling for heat, there was still steam circulating through the heaters. They didn't realize that when they disconnected the controls, and by showing them this picture, it knew immediately what they had to do. And for 25 heaters, that turned out to be a fairly significant steam demand, even during the summer, because the heaters were still energized. So they had to go and just valve out all these heaters, and that was a very easy thing to show them with the thermal imager. The next slide. One of the places where I personally like to use thermal imagers is on steam traps. Steam traps are just a persistent problem in plants where steam is being used. And it only takes a few relatively large leaking steam traps to greatly increase fuel consumption. And they can cause a lot of other more serious maintenance and operations problems in condensate systems. So in this case, we noticed at this plant that there were some very large plumes that were exiting condensate receivers. And we worked our way backwards through the system to try to figure out where the source of that excess steam was. And what we found was that there were several large traps that were failed open. The plant condensate system was overpressurized, and we calculated that their steam losses, just because of these traps, accounted for almost 40% of the total steam load in the plant. The IR camera was very helpful here, because with those large traps, looking at them from the outside, you don't know if they're failed or not. But one of the things that you can do is just simply point the camera at the trap for a period of time, several minutes or so, and the traps, if they stay the same temperature as the steam temperature on both sides long enough, what you know is that the trap is failed open. So you're getting steam passing through the trap, and a trap is not filling with water as it should, and then letting the condensate into the system. So the IR camera helped them identify which traps were failed, and it was a fairly simple matter of going in during the next maintenance period. And in some cases, they replaced the traps. In other cases, they just had to replace the internals. But nearly all the large traps that we looked at had failed open. And in this particular case, I think there were 6 traps in the plant that accounted for nearly all that steam loss. Next slide. So the final example for using an infrared camera was at a dairy processing plant. And in this case, they had a refrigeration system that was connected to a 0° Fahrenheit freezer. The plant had problems with compressors failing repeatedly on this particular system. This was kind of an interesting case, because the plant knew that they had an infiltration problem that was causing excess loads. But before they had seen the infrared images, they really didn't have an appreciation for what was going on. And what was happening was the evaporators, which were at the rear of the freezer, were operating at about -40. And they were causing very large pressure differentials on the compressor and premature failures. The front of the freezer, where the door was, and the source of the infiltration was at about 0, where it should have been. But the problem was, because of the infiltration, the evaporators and the compressors in the rear had to operate at a much lower temperature to maintain the correct temperature for the product in the freezer. one thing that we had to do here, because the infrared camera really only accurately reads down to about -4, we had to verify by other means, since the accuracy decreases below that threshold. And in this IR image, you can see that there's at the top it says approximately 25.5 degrees Fahrenheit, and that's because it's below the accurate range of the camera. So this is an example at the other end of the temperature scale where an IR camera can be useful. So the next slide, just a quick wrap up here. Even in small plants, data loggers and imagers can really help by providing an inexpensive ways to help to identify and quantify energy and maintenance problems. The data loggers and sensors can be acquired for a few $100s. Thermal imagers, you can acquire them for as little as $2,500. But the costs really outweigh, or I'm sorry, the benefits really outweigh the costs of the equipment, just in terms of the potential savings and the value of the information that the plants get. One of the recommendations that we often make to plants where we've done assessments, if they don't have equipment like this, is we recommend that they purchase a handful of data loggers and current clamps, current transformers, and acquire a thermal imager, because they can be used by maintenance departments, they can be used by engineering. Anybody who has a need for this kind of equipment can quickly set it up, use it, analyze the data, and pretty quickly get answers to questions that they really couldn't answer before. And so, speaking of questions, if there are any questions, I'll be happy to try to answer them.
Thank you so much, Ralph. It was very interesting presentation. Any questions from the audience? If you have a question, you can unmute yourself and ask the question. So can everyone hear me? Any questions?
Wow, this is an easy crowd.
I know. So a couple people in the chat are thanking you. Thank you, Ralph. Thanks, good info. Yeah, I agree. It was a great information. So I think we may have a question here. Somebody is typing. So somebody is asking, do you know of any good products other than what you mentioned for machine monitoring?
For machine monitoring, okay. Well, let me ask a clarifying question. What? Oh, motors. Okay, yeah, I saw that pop up.
Yeah, like motors.
For continuous monitoring, or for episodic monitoring, like what we do. Okay.
Continuous.
Okay, so for continuous monitoring, there that kind of brings up what kind of facility the motor might be in. But there are a lot of different platforms, software platforms and equipment platforms that that support data acquisition. For factory automation systems of all types will do this type of thing, regardless of what kind of an application it is, if it's a motor. But it usually starts with, you still have to install current transformers, so you have to put the sensors in, and then you have to tie them into a device that will log that information and then do something with it. So I can't really point to specific system manufacturers that do that. There are a lot of companies out there that will support those kinds of systems. One that comes to mind, for example, is Johnson Controls. They install this kind of equipment all over the place, often in commercial applications, but also sometimes in industrial applications as well. And there are others, Siemens Automation, companies like that can do more permanent, continuous data acquisition. And also those systems are capable of control too. So it depends on really how far you want to go with it.
Thank you, Ralph. Any other questions? No more questions? Okay, is there anything, Ralph, you want to add?
Well, actually, I have a question for the people who are on the webinar. I'm just curious what industries they might be from.
That's a great question. So I know some people are from ECU, from the College of Engineering. I'm not sure about the others. So if somebody wants to start and introduce themselves and where they work.
Hi, I'm John Batts. I'm the facility maintenance manager at Steamo in Tarboro. Take care of everything from power distribution to pneumatics and HVAC.
Okay. Hi, John.
Hey, how you?
Good. John, I'm curious, do you have a factory automation system at your facility?
To some degree, I do. My HVAC, I have an energy management system. Out on the production side, those guys have some systems they use. I'm not quite familiar with the name of them, but we've done a lot of things. We went from 400 watt meter halides to T5s, and from T5s to LED. So got about 250 some odd fixtures in the building throughout. So this helped tremendously. We went from like 60-ton HVACs to variable speed HVACs, and we also going on air compressors. As we have capital become available, we going with variable speed air compressors. I think I still have 2 fixed speeds and have 4 variable speed air compressors now. So as you say, a lot of this stuff helps a lot. It's just trying to stay on top of what's out there so we don't get too far behind.
Yeah, it's always tough in a manufacturing environment because number one is to keep the plant going.
Yes, and one thing we did do some years ago, we had a black membrane roof, and we upgraded when we needed to a white membrane roof, and we lost 40 degrees of heat at the roof. So that was a tremendous savings there alone, not having to run the HVAC so hard.
Oh wow, yeah, that's a big difference.
Yes, yeah, and I was surprised, but we went on with another piece of insulation, and when we had the old membrane taken off, we added some insulation and went with the white. It was a good savings there.
Yeah, sounds like it.
Yeah.
Good.
Thanks for the time to taking the time with us today.
Sure.
Okay, it seems there is no more questions. Thank you so much, Ralph. We appreciate your time. And this is the contact information for Ralph. The presentation will be posted, or the webinar will be posted on our center website and Facebook, LinkedIn pages. Thank you so much.
Okay, and thank you.
Thank you.
Bye-bye.
Bye-bye.